Welcome to ModPath Chat, the official podcast of modern pathology, featuring interviews with authors and experts on the latest science, technology, and developments in the field of pathology. Our host, Dr. George Netto, is the editor-in-chief of Modern Pathology and professor and chair of pathology and laboratory medicine at Perelman School of Medicine at the University of Pennsylvania. Here's Dr. Netto.
Welcome to ModPath Chat. Today's episode, we have two great guests. We'll start with the resident, Josh Lewis, a clinical pathology resident at Mass General Brigham. That's a new name, and heading to a hematopathology fellowship next year at the same place. Josh is one of those very early rising stars. He's already published in Modern Path, so he's the first author on a paper with a great group of collaborators. And my other distinguished guest is my friend and now my colleague, Olga Pozdnyakova. She's the director of our division of hematopathology here at Penn Medicine, University of Pennsylvania. Olga is a world expert in flow cytometry and hematopathology, and clearly that's the topic of the discussion today, is the recent paper published where else in Modern Pathology about automating the process of flow cytometry. So I'm looking forward to the discussion, and thank you both, Josh and Olga, for accepting my invitation.
Thanks for having us.
Thank you for having us, George. It's a great honor. So just a disclaimer, this is the first time I'm doing a podcast, so please bear with me. But I'm very, very excited to showcase the work that Josh and I did at MGB in the world of flow cytometry and how we can automate flow cytometry and how we can bring AI into the clinical space. And this is basically what we're going to be talking about today.
Wonderful.
So I don't know, if you don't have any questions, I can sort of start with an introduction. So why we decided to look at flow cytometry and why we thought it would be a good way to showcase what flow cytometry can do and how AI can help. So flow cytometry, I mean, I don't think anyone can talk about hematopathology without using the word flow cytometry. So flow cytometry has literally became the tool, the technology, the technique that is very widely used in hematopathology, in diagnosing of diseases, and not even so much as a diagnosis, but in triaging the diseases and deciding what to do with this particular specimen. So it truly became more of a screening test, as a rule-out test. So this is why I told you a little bit earlier, not as a diagnosing, but sort of a screening and ruling out. And the reason for that is because it's a very powerful technique that allows you to interrogate cells and conditions from simultaneously from many angles. So we can use right now up to 14 different parameters and antibodies in one tube to look at the cells and to decide what the cell is, whether it's a T cell, B cell, malignant, non-malignant cell. And also, so this is one reason why it's so efficient. And another one is because it's very fast, right? So the turnaround time is 1 to 2 hours, and you can immediately decide if it's a very sick patient and you suspect the patient has acute leukemia, you can in 2 hours know whether it's acute myeloid leukemia, acute lymphoblastic leukemia. But having said that, it is a very powerful technique, but it's very manual, highly manual, from specimen processing to acquisition of the specimens to analysis of the specimens. And the more data we collect, and we do collect a ton of data, so we'll call them events, and we talk about million events. So the more cumbersome the analysis becomes. So the more markers we use, the more data we collect, the more difficult it becomes. And so Josh, with his excellent training and curiosity about how artificial intelligence can help us with this analysis part. So he developed a model that helps interrogating the data, not manually, so without doing manual gating and looking at the 2x2 plots, but how to do it using the raw data from the specimen.
Wonderful background. And for somebody who was worried about first-time podcast, It's a good turnaround. No, I'm not surprised.
Oh, no, thank you. Thank you.
So Josh, let's get to the techie part, which usually that means younger generation need to help us. But, so tell us about the model you use, deep, the neural, I think learning model, deep learning model, and how you designed the cohort and what have you. Just briefly, hopefully.
Sure.
In a simple way, please.
For sure. Well, I can start by mentioning that other groups have looked into using statistical and machine learning approaches to analyze flow cytometry data before, but we recognize that there are some significant shortcomings in these approaches. For example, a lot of groups have looked into using these approaches for population identification, for finding individual populations of different cells of interest, say whether they're B cells within lymphoma cases or plasma cells within myeloma cases, but these kind of fall short in terms of making an automated diagnosis and still require a lot of manual steps. And then lately, there have been some groups looking at using the bivariate plots from flow cytometry reports and feeding those into machine learning algorithms to make predictions. But as you can imagine, once you go from the raw data from the flow cytometry and convert those into those bivariate plots that really just show the associations between two different flow cytometry markers, you lose a lot of data, a lot of information in that step. And thus, we thought that the performance of those models wouldn't be quite up to par as if we built models that analyze basically the raw data that come directly from our flow cytometers. So the approach that we took, it has a fancy name, but I'll break it all down. It's called attention-based multi-instance learning. So this, for someone who may not be familiar with these approaches, it might seem quite scary, but it's actually quite a simple once you break it down a little bit. So machine learning in general is basically training a statistical model on the computer to learn from a bunch of data. So at Brigham and Women's, at the hospital that we work at, we have a lot of acute myeloid leukemia cases that come through our hospital. And so we're able to leverage that data and kind of build a statistical model to learn, what associations these different flow cytometry markers have, either with the presence or absence of acute myeloid leukemia, differentiating between different types of leukemia, starting to predict the presence or absence of different cytogenetic or molecular aberrancies. So that's kind of all falls within the realm of what machine learning is. The multi-instance learning is a subset of that. So for those who are maybe familiar with flow cytometry, basically how it works is we capture information from thousands, tens of thousands, almost hundreds of thousands of different cells from a particular patient sample. We're able to get information about the expression of different cell surface markers, as well as forward and side scatter, which give us information about the different physical properties of these cells. And basically what multi-instance learning is leveraging information from all those thousands of events, but then integrating it into a single diagnosis. So ultimately, we want to come to a single diagnosis for a particular patient, whether or not they have leukemia, for example. And then attention-based learning is something that's become very popular over the past few years. Basically, it allows us to give specific attention to individual events or cells of interest within our sample. So for example, when you're trying to diagnose a patient with, say, acute myeloid leukemia, you might be more interested in analyzing the immunophenotype of myeloblasts compared to other cell types that may be in the sample, but may not give as much importance for this particular diagnosis. So the machine learning algorithm can actually learn what associations different cell types or different events within the sample have towards making these predictions. And this approach has actually been used quite a lot within the anatomic pathology realm for using scanned images of pathology slides and finding which areas of the slides kind of correlate or are predictive for certain diagnoses in patients. But really, this hasn't been applied too much at all in the clinical pathology realm or towards flow cytometry. So to our knowledge, this is quite a novel approach for analyzing flow cytometry data, but as we showed in the paper, we were able to get quite promising and exciting results from these types of models.
Excellent. So, and I refer our audience, of course, you guys have to read the paper. It's such a relatively complicated issue, although Josh just made it sound very simple, and I love that. But my understanding is, so you talked about the weighting. That's the features or the attention module give. You do that on on two tubes. Is that and then you integrate these weights of the different parameters, and you end up with your prediction model. Is that's how? So how explain to us why two tubes and what's the difference? Just more cells, more events. What is the
Sure.
advantage here?
At least at Brigham and Women's and commonly at other institutions as well, a lot of our flow cytometry panels utilize more than one tube of different cell surface markers to get better an understanding of the immunophenotype of the cells of interest. So, for example, for us, we have one tube that has mostly myeloid markers that might be important, especially for patients with acute myeloid leukemia. And then we have another tube with more lymphoid markers, which might be more important for...
The markers are different. It's not because I didn't understand whether there was a duplication or now it makes sense. And then you decide between these markers what are important and you integrate. And exactly. So I realized you did a lot of patient, a lot of sample, 1,820, and half have disease, half don't, and so all that. So the first model was just to tell or trying to see, is it positive for leukemia or not, right? And then another bifurcation. Can you explain how the steps work?
Sure. So we wanted to go down the route of how a typical hematopathologist would approach a particular flow cytometry sample of interest. Once they get it in their queue, what are the usual steps they do towards making a diagnosis? So usually, and for a leukemia case, you want to most importantly differentiate whether the patient has an acute leukemia or not. So that was kind of the first model we did. Part of it was more of a proof of principle because in most cases, a hematopathologist can manually do this quite accurately. But we wanted to show that this type of approach, which hasn't been used before for flow cytometry data, can perform quite well. And we were able to show that our model can accurately differentiate cases that don't have any acute leukemia versus those that do. And then among those cases where the model predicts that there is the presence of acute leukemia, then it's able to further differentiate that. So the next step a pathologist would take is whether this seems to be more of an acute myeloid leukemia versus like a lymphoblastic leukemia, whether it's a BALL or TALL. So that's what the model then does. It differentiates the AML versus the ALL cases. And again, it performs quite well in this case, as we would expect. We know a lot of the immunophenotypic differences between these two entities. And so we expected that the models perform quite well. And the really exciting part in my mind is kind of the next step is that the models are able to take in terms of being able to start predicting what type of cytogenetic and molecular aberrancies these particular AML samples have.
And we'll come to that in a second, but I just want to emphasize how well the model. So you use the area under the curve, right? A ROC curve analysis and showing. So how well did the model do as in terms of like 0.96 ORAC, and what does that mean in terms of? So it's very sensitive and very specific and
sure.
Yeah.
Yeah, there are a few different ways you can approach analyzing the performance of different machine learning models. One commonly used statistic to compare model performance is the area under the receiver operating characteristic curve, or the AUROC. Basically, how this works is you order your different samples based on the predicted probability of whether a case is acute leukemia or not. And then you compare that to its actual classification. And once you do that comparison, you're able to draw an ROC curve. And the closer the area under that is to 1, the better your model performs. So there's no really set thresholds of a good versus or poorly performing model, but typically cases that have an AURC as close to 1 as possible perform quite well. And ours did perform quite well. Our model of differentiating the presence or absence of acute leukemia had an AURC of 0.961. That differentiating between AML and ALL is 0.965. We also showed that the model had both good sensitivity and specificity, which is important because especially if we want to use this type of approach in a triaging role, it's kind of a first pass before an actual hematopathologist then further analyzes the data. We want to make sure that we're continuing to pick up samples that we think might have the presence of an acute leukemia.
Yeah, no, that's exactly, Josh, what I just wanted to highlight is that how do we put it in clinical use? So why we're so excited about it and how it could be utilized in clinical use is, as we mentioned at the very beginning, it's a very manual process. And not only that, because it's so complex, like everything in hematopathology, it requires a lot of training to analyze the data. And very often it's technologies they run, so it's flow cytometry is a clinical pathology test. So the technologists, they run the data, but they are not necessarily either very familiar or very experienced in the analysis of the data. But what in terms of to increase efficiency, so we would like the algorithm to start analyzing the data as the data being acquired, so that the technologist as a next step knows, oh yeah, this is a negative sample and I can stop, or no, it's a positive sample. And then my next step is going to be to triage and decide whether I need to use myeloid markers or I need to use the lymphoid markers to come to a diagnosis and prepare the case for a hematopathologist.
So you can see how that increase efficiency, improve turnaround time, and even cost potentially, because the time of the technologists and all the agents. Wonderful. So now we move in, which is fascinating. And I like your analogy when you were talking about images, scanned images of an H&E slide, whole slide image. How every point or every point of data or event get integrated in that model. But we all know now that there are models where you look at the H&E image at that scan and can tell you, infer the molecular driver of this specific lung cancer, for example. So what you did here is very similar, and you build models for every potential, for all the high incidence, I guess, translocations, fusions, and variants, right? So share with us.
Exactly. So we built models that tried to predict the presence or absence of 9 different cytogenetic aberrancies and then 32 different molecular variants in different AML cases. The goal is kind of see, we didn't expect that all these models would perform really well, but we wanted to see for what particular cases we could actually infer useful information about the immunophenotype of these cells from flow cytometry to start making predictions, and in some cases quite accurate predictions about the molecular phenotypes of these cases. And this is somewhat done manually as well. We know that there's certain immunophenotypes characteristic of things like acute promyelocytic leukemia with PML rare translocation. We also know that there are certain aberrancies associated with, for example, mutations in the NPM1 gene that we can sometimes see in AML. But really, this type of study hasn't been done across a wide range of different cytogenetic and molecular aberrancies. So we tried to see whether there's some other interesting genes or translocations that we're able to get models that are able to predict quite well whether they have those variants or not.
And it did that. So you're saying even for stuff that usually, Olga, you by looking at the immunophenotype, you can guess, but there are certain alterations that you cannot guess, and the model did good in those even. Wow.
Yes, no, it did. And I mean, both of you talked about also morphology of the cells. So I think as the next step, it would be, I mean, again, we would never look at the immunophenotype without looking at morphology. And I think for this model to perform even better, similar data could be collected from the cell morphology, so how the cell look. And so then you combine the cell image, its beautiful profile, along with the immunophenotypic data, and then voila, you have your diagnosis with underlying genetic abnormalities. It's like having real ID.
Excellent.
With a genetic signature, right?
Right. So, and that's clearly, if you get it to almost perfection, you can see how much. Again, don't have to wait on NGS. Even in the best of places, these things take a week or two. So you can see the huge value of that. Josh, but one question. So technically, is it a 41 models, because you mentioned 9 cytogenetics and 32 variants? So how in reality you do it? You run it with one model first, and then you go with the most likely, or you have to run all 41 to explain to a simple-minded person like me?
Sure. It's actually broken down into 2 different steps. The first step is something called pre-training. And what this does is you have a neural network, a machine learning model, and you try to expose it to as many different cases as possible that it might be able to extract some kind of useful information from. You're not yet telling it to make any type of diagnosis or any classification, but you're basically just exposing it to information that it might be able to use later. So that type of process is called pre-training or self-supervised training. Basically, we expose our model first to all 1,800 AML cases that we had come through our laboratory over the past 3 years, that have the models kind of learn what basically a flow cytometry panel looks like. What do these events look like, and kind of get the gist of what these types of samples look like. So then you can then hone in on specific applications of interest. So then once you do that pre-training procedure, then you can use that for multiple different applications. You can then shift that towards, for example, predicting the presence of a 1517 translocation, or predicting the presence of an NPM1 mutation. That requires something called fine tuning, or we're not fully training a whole new machine learning model, but we're kind of fine tuning it towards a specific application of interest.
Excellent. So, but after you do all that, now we got it to a sample, and now you're validating, or real life. Do you have to run every model of your 41 to know which exact translocation or which exact variance, or it does it all at once? That's awesome.
Sure. At this point, yes, but we do have a lot of interest. For example, although these models don't take very long to run, you can imagine that as we build more and more models, that kind of the time it takes to perform this analysis could increase significantly. And as Olga mentioned, the whole point of this was to create an automated analysis approach that works in a timely fashion. So we are exploring possible ways that we could have the model have multiple different outputs about the presence or absence of multiple different cytogenetic molecular aberrancies just from running one single model versus multiple different individual models.
Well, if you do that, please send the paper to Modern Path, and you'll get another podcast, I promise you. Wonderful. So let's finish up. This is so enjoyable. Olga, tell us, how do you see, I know you're passionate about digital and applying AI to your field. How do you see that really becoming used in day to day, and basically triaging negative cases?
I truly believe that, George. And I know that there is a irrational fear out there that the machines will substitute pathologists and hematopathologists, and there won't be any work for us. And that's not the case. They'll always be as good as the machine learning is and our algorithms are. There is always going to be a complicated case where a human eye, believe it or not, would perform better, right? A human mind would perform better. But a lot of what we do, and I don't know, I don't want to put percentage on that, but say 90% of what we do is pretty routine run-of-the-mill cases. And I always use this phrase, let AI do simple work, right? So if it's a negative case, yes, we will still look at it, but it could be similar to how we approached CBC and hematology analyzers, right? We don't look at negative cases. We let the machine go out with the automated differential and everyone accept us as a norm. So I want for flow cytometry to do the same, to have this paradigm shift that if it's normal, I want it to perform at the same level as a CBC with AutoDiff. I want it to be looked at by a technologist and then let go of it, because there'll be a lot more complicated cases that will require a lot more time. And we would rather spend this time looking at these complicated cases rather than just looking at routine negative cases. So that's how I view it. I know that some people may not agree with me on that, but I've been in the clinical pathology world for a long time, and the technology has developed and has really made huge strides towards the next generation technology. And I think this is all achievable.
All right. Well, definitely AI is not going to replace any physician. It's, as Dr. Deliva said a few years ago, it's the physician with AI is going to replace that physician that refused to learn any AI, or at least listen to smart people like Josh and learn a little bit about AI. So this way we have our job security. Thank you both for the most enjoyable discussion, and wish you the best, Josh, with your fellowship. And just imagine when you finish your fellowship and all that, what you can do if you've already achieved such great studies as a resident. So thank you both.
Thank you
Thanks so much for having us.
Thank you, George.
Any opinions expressed in this podcast are the speaker's own and do not represent the views of Modern Pathology, Elsevier, the University of Pennsylvania, or USCAP. Your ModPath Chat host and scientific director is Dr. George Netto. The producers are Dr. Catherine Ketchum and Carly Hess. Technical direction is provided by Kaminsky Productions. Music by Mitch Neubauer. Thanks to the authors, reviewers, and editors of Modern Pathology for making this podcast possible.